In today's lesson, we're going to look at how to describe simple harmonic motion mathematically. So in the previous video, we went through kind of what it is, and one thing you should be familiar with are these three graphs. So this first graph would be a graph of the displacement of an object against time. Now remember that to get velocity, we just take the gradient of a displacement against time. So here the gradient is 0, and that's why we get a value of 0 here on a velocity time graph. And again, the gradient of a velocity time graph gives us acceleration. So here where the velocity gradient is large and negative, that's why I get a large and negative value over here. Now, what we're going to try to do is to come up with a mathematical description of what we see here. And hopefully what you can see from looking at this is, well, first of all, this looks like some kind of cos graph, and it is a cos that changes with time. Now, the next thing we can say is, well, what about the amplitude of this? What about the maximum value this takes? Well, what we can do is we can say, because simple harmonic motion always has an object returning to the same displacement, I'm going to say that the maximum displacement is x naught. That's the amplitude of oscillation. So I can say that the position x against time is equal to x naught times some function of time. The next bit is what really goes in here. Obviously I can have faster or lower frequencies. So the easiest thing to think about here is, well, I know that angular frequency is 2 pi over t. And I can say when little t is equal to the time period, then that is when it has done one full oscillation. So I can say that at any point in time, the angle that something has moved through is omega times little t. So what I will say is that the displacement at any point is equal to x naught cos omega t, where omega is 2 pi over t. So therefore I must be using radians for this to work. Now I could also say exactly the same way, x is equal to x naught cos of 2 pi ft, because I can say that omega is also equal to 2 pi f, which we've done in an earlier video. So any of those things you can write. This is the one that we normally use. Sometimes it's useful to use this form as well. Now velocity, we talked before, we said there's different ways you can do it. You can do it by differentiating this if you're happy with that, or you can just look at it by symmetry. You can say, well, this is the same as saying, well, this is a negative sign, which again has the same x naught here. It's proportional to this x naught, but obviously this would be the maximum velocity at different points. So one easy way of saying it is v is equal to v naught sine omega t. So it would actually be minus v naught sine omega t, because we can see here where at this point here where it's large and negative, this becomes large and negative, so it becomes this is a minus sign graph. Or you can prove it with maths, and we've done this in the previous lesson. Rather than in terms of v naught, we can say v is equal to x naught omega sine omega t. And again, this is the most common form of it that you will see. If you looked in the previous video, sorry, minus sign there, you can see why we get this omega form coming out. You can kind of see it experimentally as well. Hopefully you can see if I was to crush this up a little bit, then the steep bits would get even steeper. So it does depend on omega. But to really mathematically prove it, you have to use the calculus from last lesson. And then finally, the acceleration. Well, acceleration is just the mirror image of this one. So again, I'll have a naught, so I can say a is equal, acceleration is acceleration naught times minus cos, so that would be a is minus a naught cos omega t, or again, more commonly, I would say a is equal to x naught omega squared cos omega t. And once more, this is the most common form of the equation. So these three are used to describe mathematically how something is moving in terms of displacement, velocity, and acceleration. And there we have those summarized at the side. Now, often you're asked to think about the energy that goes on in simple harmonic motion. Now, if you imagine, if we go back to these graphs, we can see that when it is at its maximum displacement, it has its largest velocity. And similarly, when it has zero displacement, it has when it has its largest displacement, it has its zero velocity. When it has its smallest displacement, it has its maximum velocity. Now, if you think back to different examples of it, that kind of makes sense. If we imagine a pendulum as it moves backwards and forwards, a pendulum is moving back and forth between these two positions. So there is a change in its gravitational potential energy. That's really the energy exchange that's going on. So over here, it has maximum kinetic energy. It's moving very quick. Sorry, it has maximum GPE, gravitational potential energy. It has zero kinetic energy. As it swings through the center, here it has maximum kinetic energy and it has zero potential energy, or minimum gravitational potential energy. So if we think about this in terms of displacement, we can say when anything in simple harmonic motion is at its maximum displacements, that's when it has the maximum potential energy. For anything undergoing SHM, as it travels through the center of oscillations, it always has zero kinetic energy, or zero component kinetic energy from SHM. It might be moving in a linear fashion, say, and that could give it a constant amount of fixed kinetic energy, but that's quite a niche case. Usually we just say it's zero kinetic energy. Now, what we can do then is we can say, well, what is the total energy of this object? And there's a really simple little trick we can use. We can say, well, at any time, the total energy is equal to the potential energy, or whatever form that takes, plus the kinetic energy. But when it's over here, we can when it's at its zero displacement, so I can say at x equals 0, I can say always the potential energy is 0 and the kinetic energy is maximum. So when kinetic energy is maximum, I can say that the kinetic energy will be equal to a half m v naught squared, because kinetic energy is just half mass velocity squared. V naught is the maximum velocity. So that is going to give me its kinetic energy at maximum point. If I want to think about, well, what is V naught? What is the maximum velocity? If I come back to this equation, when will this be maximum? This will be maximum when sine omega t is 1. The biggest that sine of anything can be is 1. So let's just let sine equal 1. So I can say that the maximum kinetic energy then will be a half m times the biggest this can be. So that will be minus x naught omega times 1. And I need to square that because that's velocity. Now when I square a negative number, it always becomes positive. So that becomes a half m x naught squared omega squared. Now, I've also said that the maximum kinetic energy is equal to always the total kinetic energy. Because the total kinetic energy never changes, therefore I get this equation that I can say the energy, which I'm going to write as E0, because that's the total energy at all times of any object undergoing simple harmonic motion, that will be a half m x naught squared times omega squared. And this is a third key equation for you to learn. This tells me that so long as I know the amplitude and the angular velocity of an object, I can always find its kinetic energy, its energy, and that energy will stay the same at all times. So this also tells me, well, what is the maximum potential energy? Because when the kinetic energy is 0, all of the total energy comes just from the potential energy, so the maximum potential energy will also be a half mx naught squared omega squared. All right, now one last equation. We're going to try and prove this equation here. Now this is one that you just need to know. It appears in your exam that we can say that the velocity at any point is equal to plus or minus the angular velocity multiplied by the square root of its amplitude squared, take away its position at a moment in time squared. But I'd quite like to try and show you one way of proving this equation. Now this is a little bit tricky. You don't actually need to be able to prove it. There are lots of other proofs as well that are more mathematically rigorous, but this is one way just to prove this isn't magic. So we're going to go back to our mass on a spring, and we're going to think about this oscillating up and down. Now, what we're going to say is, because I know that the total energy always stays the same, therefore I can say the total energy initially, so total energy at the start, is equal to the total energy at a final point, at any endpoint. Now, that is made up of kinetic energy plus potential energy at all points. So I can say the initial kinetic energy plus the initial potential energy is equal to the final kinetic energy plus the final potential energy. Now mathematically then, kinetic energy of this object will be a half mv squared plus, and then I need the energy stored in this spring. So if you think back to year 12, that is a half kx squared. And so that will be the initial and the initial, so the initial velocity and the initial displacement. That is equal to a half mass times the final velocity squared plus a half times the spring constant times the final extension squared. Now what we're going to say is, let's take it when the kinetic energy is 0. So let's take it at the point where it's down here at the bottom. So if I say that when the initial kinetic energy is 0, that occurs when the initial velocity is 0. So I can say VI is 0. Now when that happens, I can also say that the initial extension, therefore, must be the amplitude, because we get 0 velocity when the extension is maximum, looking at this graph. So therefore I can say, well, v is 0, so this term all just collapses to 0, plus a half kx naught squared, and then I'm just going to let this be at any other point. This is at any point later in time, so I'll say this is equal to a half mv squared plus a half kx squared, where x is my position at any point, v will be a velocity at that same point. And I've been asked here to find v, so I just need to make v the subject of this equation. Well, my halves cancel straight away. So I can get mv squared is equal to kx naught squared minus kx squared. Let's collect the terms. I can say v squared is equal to k lots of x naught squared minus x squared. Now I'm starting to look good here, sorry, m of v. If I divide both sides by m, I get v is equal to k over m lots of x naught squared minus x squared. Now, the clever bit is, if you remember from square root from way back, from previous lecture, I'm not going to go through it now, but we did prove that omega is equal to k over m for a mass on a spring. You can go back and rewatch that if you don't believe me, but we definitely did it. Sorry, that's omega squared is kx over m. There we go. Omega squared is k over m. So I can say v squared is omega squared lots of x naught squared take away x squared. If I square root both sides, then the square disappears from that term and I get square root of this term. And hey presto, there is my final equation that I need to know today. Now this derivation isn't necessary for your A-level, but it's a really cool one to just show how this works. And a fun exercise is, can you do the same thing, but for a pendulum? Can you prove this equation still works? That's a nice little exercise just to try. But that is the mathematics of this. So you need this equation here for velocity at any given point, given just the angular velocity and the amplitude. You also need these three terms here for displacement, velocity and acceleration in terms of angular frequency. And you need this term here, which is wrong on my slide. I need to add in an m term there, but this one's right. You need to know the term, the equation for the total energy of an oscillation. All these things should be clear in your head before you go and sit your exam.